Can you juggle a jam-packed schedule and still find enough rooms for every meeting? Meeting Rooms 2 is a Pattern Mastery 100 favorite and a must-know at Google, Amazon, and Meta. Over 35% of candidates get tripped up by overlapping intervals and efficient resource tracking. Master this, and you'll be set for any scheduling, heap, or interval-based interview problem.
Let's break down Meeting Rooms 2 using the basic approach, so you can solve any resource allocation or interval overlap challenge step by step. You're given an array of meeting time intervals: start, end. Return the minimum number of conference rooms required for all meetings. List of intervals, unsorted, each as start, end. Integer, minimum number of meeting rooms needed. Picture running an event center. How many rooms do you need to make sure every meeting can happen without conflicts? Interviewers might ask, how do you efficiently track the maximum number of simultaneous bookings in a day? What's tricky? Intervals can overlap in complex ways. Tracking active meetings efficiently is key. Use a min heap to always know which room is free next. Sorting is crucial for an optimal solution. Sort all intervals by start time. Use a min heap to track meeting end times, smallest end time on top. For each meeting. If the current meeting starts after the earliest ending meeting, that room is freed, pop from heap. Otherwise, allocate a new room, push end time to heap. The heap size at any moment tells you how many rooms are in use. Let's clarify. Heap contains the end times of all ongoing meetings. Always pop from heap when a room frees up, i.e., when a meeting ends before the next starts. Edge cases. No meetings, 0 rooms. All meetings overlap. Need as many rooms as meetings. Sort intervals by start time. Initialize a min heap, priority queue. For each interval. If heap is not empty and interval starts greater than or equal to heap 0, earliest end, pop from heap. Push interval's end time onto the heap. After all meetings, heap size equals rooms needed. Time complexity for this approach is O(n) log n, because sorting dominates the runtime, and heap operations cost log n per interval. We use a method called min heap of n times. First, we sort all meetings by their start time. Then, we use a min heap to always track the earliest ending meeting. If a meeting room becomes free, its end time is less than or equal to the next meeting's start time, we reuse that room. Otherwise, we need a new room. So we add a new end time into the heap. In our Java implementation, we start by defining the solution class. It's just the container for our method. The function min meeting rooms takes a list of meeting time intervals and returns the minimum number of rooms required. We sort all meetings by their start times, lining them up in the order they begin. Next, we create a min heap, which always gives us the smallest end time first. This helps us quickly check which meeting room frees up the soonest. We then loop through every meeting, one by one. For each meeting, we check if the earliest ending meeting in the heap finishes before the current meeting starts. If yes, that room is free, so we remove it from the heap. We're effectively reusing that room. Then, we add the current meeting's end time into the heap, assigning a room for this meeting. Finally, the number of rooms we need is simply how many end times remain in the heap, since each end time represents a room currently in use. And that's how this algorithm works. It first sorts the meetings to get them in order, then uses a min heap to efficiently track which rooms are free and which are still busy. Efficient, simple, and elegant. This approach handles each interval at most once, and the heap never grows beyond the number of overlapping meetings. Worst case, if all meetings overlap, the heap grows to size n.
Let's test the function with intervals, 0, 30, 5, 10, 15, 20. Meeting 0 to 30 goes in the heap, 30. Meeting 5 to 10 overlaps push 10, 10, 30. Meeting 15 to 20 starts after 10 ends pop 10, push 20, 20, 30. Heap size is 2, so we need 2 rooms, and the program outputs exactly 2.
The time complexity of this approach is O(n) log n, dominated by the sorting step of the start and end arrays. We solve the problem using a 2-pointer strategy on separate arrays of start and end times. First, we extract all start times and all end times from the given meetings. Then, we sort both arrays, start times from earliest to latest and end times from earliest to latest. Next, we initialize 2 pointers. One pointer iterates through the start times, and the other iterates through the end times. We also initialize a counter to keep track of the number of rooms needed. As we loop through the start times, if the current meeting starts before the earliest ending meeting finishes, we increment the room count because a new room is required. Otherwise, a room has become free, so we advance the end pointer to indicate that a room is now available. This continues until we have processed all start times. In Java, we begin by defining a class called solution that contains our method. The min meeting rooms method calculates the minimum number of rooms required. If there are no meetings, the method immediately returns 0. We then determine the total number of meetings and create two arrays, one for start times and one for end times. We loop through each meeting, storing its start time in the starts array and its end time in the ends array. After populating both arrays, we sort them to prepare for the timeline comparison. With the sorted arrays ready, we set two pointers, S for the start times and E for the end times, along with a room counter. We iterate through all start times. If a meeting starts before the earliest ending meeting finishes, we increment the room count. Otherwise, a room has freed up, and we advance the end pointer. We then move the start pointer forward to the next meeting. After processing all meetings, the room counter reflects the exact number of rooms required. This algorithm works by first arranging all start and end times in order, creating a clear timeline. The two-pointer traversal efficiently tracks overlapping meetings and available rooms. It is a simple, elegant, and efficient solution that avoids additional data structures while solving the problem clearly. Sorting the arrays costs on log n, while the pointer walk through the arrays is linear on. This approach is easy to understand and demonstrates the logic of handling overlapping intervals without heaps, making it ideal for teaching how to manage meeting schedules efficiently.
Let's check how our solution figures out the minimum number of meeting rooms using this test case. The input is 7, 10, 2, 4. Each pair shows when a meeting starts and ends. We sort the start times 2, 7, and the end times 2, 4, 10. The first meeting, 2 to 4, uses one room. The next meeting starts at 7, which is after 4 ends, so we reuse the same room. Total rooms needed is 1, and the program outputs exactly 1.
Breakdown recap. We're given an array of meeting intervals, each with a start and end time, and we need to return the minimum number of rooms required so that all meetings can happen without conflict. In short, it's all about finding the maximum number of meetings that overlap at any point in time. Assess recap. The challenge is tracking overlapping intervals efficiently. Instead of checking every pair, we sort the meetings by start time and use a min heap to keep track of ongoing meetings by their end times. The heap helps us know which room will be free next. If a new meeting starts after the earliest one ends, we pop it off the heap, that room is now available. Otherwise, we push the new meeting's end time, meaning we need another room. The heap's maximum size during the process tells us how many rooms are needed. Structure recap. We start by sorting all intervals by start time. Then, we initialize a min heap to store end times. For each meeting, if the heap isn't empty and the current meeting starts after or exactly when the earliest one ends, we free that room by popping the heap. Then, we always push the current meeting's end time. Once all meetings are processed, the heap size equals the number of rooms required. Implement recap. We implemented this using Python's heap-key module. It ran efficiently, with a time complexity of log n, from sorting and heap operations, and passed all tests smoothly. Check recap. We verified the logic using multiple test cases. For example, 0, 30, 5, 10, 15, 20 needed 2 rooms, while 7, 10, 2, 4 only needed 1. Even edge cases like no meetings or fully overlapping schedules produce the correct results. Closing insight. The key takeaway? When dealing with overlapping intervals, sorting plus a min heap is a powerful combination. It's not just about detecting overlaps, it's about managing them efficiently, one meeting at a time.